and we will start working on homework 1 a little bit. I'll spend about 15 minutes before we continue with the lecture. Okay? So how did you feel about homework 1? It's kind of fairly easy, just kind of warm up. Anyone started on homework 2? Okay. Yeah, you will notice that the my descriptions of the problems tend to be very verbose, but that doesn't mean the problem is very difficult. I'm trying to set up realistic examples in these homework so that you learn from them and you see the application of numerical methods. But don't be scared by the fact that there's like a 2-paragraph description for a given problem. Okay, that's definitely the case in homework 2, problem 1. And I know there are solutions floating around. I don't care. You copy the solution. You don't. It's going to be your loss. You're going to be the one who doesn't learn something. Okay. So anyway, it's up to you. Okay. All right. Let's look at homework 1. Okay. Homework 1, introduction. So problem 1, problem 2, no one submitted anything on those. Okay, so we start with problem 3, and let's hide this guy. Okay, the second derivative of a function f of x can be approximated numerically as f double prime x is fx plus h minus 2 fx plus fx minus h over h squared. Okay, that's an approximation. That's like one definition of a second derivative. In the limit as h approaches 0, you'll get an exact derivative for sure. But numerically, h is a very small value. H is a value set by the user that determines the accuracy of the derivative. Larger values in h are expected to produce large errors, while smaller values of h will produce consistently smaller errors. For the function f of x equals sine 2x, compute the true error in f double prime of 2 using h equal 0.1 and 0.01 and comment on your results. So what are we supposed to do here? We're going to get the true value of f prime of 2 by essentially taking two derivatives of sine x. So a first derivative would be 2 cosine x, and a second derivative would be minus 4 cosine 2 sine 2x, and then 2 cosine 2x minus 4 sine 2x for the true value of the second derivative. And then we're going to do numerically, we're going to implement this function and compute the true error and comment on the results for the difference between h.1 and 0.01. All right. Okay. Right, so let's open up a Jupyter notebook. And if you're not able to see the code way in the back, let me know. We can increase the size a little bit, the font size a little bit. So essentially, we want to compute the error in f double prime 2 using h equal 0.1 and h 0.01. First, let's get the exact second derivative. So I'm going to import the sine function from the math module. So I do from math import sine, okay? And then x, I define x is 2.0, and then true value is equal to minus 4. We just computed the true derivative, right? Sine 2x, first derivative is 2 cosine 2x. Second derivative is minus 4 sine 2x, okay? And I can simply just compute this. 2 times x, okay? And then print the true value. So we get 3.0272, whatever, okay? That's the true value. All right. So now the gist of this problem is to compute the second derivative, okay? So we can do this in one of two ways. You can either just directly inject the sine function just right over here, okay? And that's one way of doing things. Or you can define a function that computes the second derivative and pass any other function to that to compute second derivative. So that would be the programmer's way of, the elegant way of doing things. But let's do the first way, the brute force way, where you just hard code this solution, this formula directly. Okay? So let's say for h equals 0.1, we set the value, and then approximate value 1 is equal to, what was this? F of x plus h minus 2f of x plus f of x minus h over h squared. So I'm just going to write this down directly. So that would be sine. So our function f of x was sine 2x. So f of x plus h is sine 2 times x plus h in parentheses, okay? Sine 2, okay, whoops, times x plus h, agreed? So that's the first term, minus 2 times f of x, which is sine 2x, okay, plus sine of 2 f of x minus h, so that's sine 2 times x minus h. Agreed? Okay, so that gives us the numerator over h squared. So notice what I do, I divide by h and then divide by h, because I don't like to put too many parentheses. Rather than putting over open parentheses h squared or over h squared, I just divide by h, divide by h. Okay, and that gives you a value for h equals 0.1, and we define error, true error 1, that's capital E, and that's the absolute value of approx val 1 minus true val, okay? And for h equal 0.01, that's the same thing. We just repeat the same approximate value 2. So that's using Python as a calculator, okay? It's not the best way to do things. And then print E1. Oops. It's my computer, it's not my typing. Okay. And then print E2. So let's change this guy to E2. And it gives us these two errors. Now, what I really care about is the ratio between these two errors. So, you know, forget about how we computed this, whether it was a brute force or an elegant way. This doesn't matter. What matters now is the difference between these two errors, okay, with the different values of h. So this is for h.1, and this is for h.01. And the error went from 0.01 to 0.0001. So cutting h by a factor of 10 cut the error by a factor of 100. Okay? We will later learn that this is what we call a second order method. If you cut your spacing by half, your error will be cut by a factor of 4, okay? Or by h squared. Okay, so we cut h by a factor of 10. The error was cut by a factor of 100. Okay, that's h squared. That's 10 squared. Okay. Anyway, we'll learn about this once we get to finite difference methods. Okay. Now, a more elegant way of doing this is to define a function. Define a function for the second derivative approximation. Okay. So I'm going to call this function d2f. That's for second derivative of a function f. Okay. Now, what would a function like that need to compute a second derivative? The way to think about functions in Python or modules or algorithms is it's a box that takes an input and produces an output, one or more outputs, okay? One or more inputs. So if you think of the function that computes the second derivative, what inputs and outputs does it provide and need? Okay? Yes?
It needs a value for x of h, and then it provides a value for what f prime.
F double prime. F double prime of x. Yes, but you're missing one input.
We could also define the function in the input.
Yeah, so it also needs the function in the input. Tyler?
So
Yeah, yeah. So you got it. We need x and h. We need the value for x. We need the value for h. But we also need the name of the function, right? To make it as general as possible, I want to be able to pass to my function any kind of basic or arbitrary function I define, right? What if I want to pass the cosine function to it? What if I want to pass the exponential function? I want my function, my Python routine. We can get confused by using the word function over and over again. We need our Python routine to be able to work on an arbitrary function, right? So I'm going to define my Python routine. Let me see if I can increase the. Is this better? Okay. So I'm going to define my second derivative routine to take an arbitrary function f, to take a point x, and the spacing h. And now simply, all I have to do is return the formula that I just gave you, which is f of x plus h minus 2 times f of x plus f of x minus h over h squared. Okay? Isn't this beautiful? Now I claim that this function can operate. Yes?
So it asks for sine of 2x, correct? So if you can put sine for just f right there, how do you integrate? Can you integrate the 2?
Yes. So Python, like MATLAB, will allow you to just pass the name of a function, and it will automatically take the argument. Now, this is limited to a function that takes one argument, okay? As long as your function takes one argument. So as long as your function f can do this operation, then things work, okay? If your function, I mean, this is a little bit advanced. If your function takes 10 arguments, this is not going to work, okay? But for our intents and purposes, this is good, okay?
When you say you can pass a function,
Let me show you, and then you ask me, okay? So here's what I'm going to do. d2f of sine at 0.1 and h 0.01. Pardon me? Yes?
Our function that we're trying to find the second derivative of is sine of 2.
Okay. Okay. So let's try. Hold on. Yeah. Your question.
you can pass a function that you create.
Yes, that's what I'm getting into. That's what I'm getting into. You're all kind of jumping the gun over here. Okay? Just follow with me. I usually will try to, I can be a little Nostradamus. I can know what your questions are going to be given, the years of, but then there's always like about 5% of questions that that will be new. So just bear with me and see what I'm going to do. Okay? So now for elementary functions f, that's great. But how do we pass a function signature for sine 2x? Okay, how do we do that? Well, we define another Python routine that defines sine 2x. Okay? So here's what I'm going to do. Because obviously, I cannot pass sine 2x over here. It's not going to work. Doesn't make sense. Okay? It needs a function signature or a function name. Okay? Sine 2x is not a function name. There's not a function called sine 2x in all of Python or the math module. What do? We create one. Okay? So what I'm going to do here, I'm going to create another function, def sine 2x. Okay? And that function, what does it take? X. Yes. And what does it return? Sine 2x. Yes. Return sine 2x. Now, okay, I defined this. Now this has become a function signature for sine 2x. Agreed? Do you now see how, if I pass sine 2x now, look at that. So now what Python does, in this d2f, it says, oh, f is a name called sine 2x. Where is it? Is it defined? Yes, it's over here. It's sine 2x. So it replaces the word f, the letter f, it replaces it with sine 2x. And then just simply puts in these arguments in here and does the calculation. Yes?
What would happen if you tried to, or accidentally passed in something that's not a function or
If you
So, for example, if you try to call that function, but you put in a 2 in the f position instead of an actual function.
it's not going to work.
Okay.
It won't work, yeah. Because the operator, the parentheses operator needs to be defined for the function, okay? You're getting into a little bit advanced nomenclature. But yeah, as long as your function implements the parentheses operator, it doesn't matter what you pass to it. You can pass it a class even, okay?
So that
So-
notation of f parentheses is effectively the call function f on what's
Yes, exactly, exactly. Okay? Now, how cool is this, right? So now we can apply this to pretty much anything. And that would be an elegant way of doing this. That would be the programmer's way of thinking about this problem, of not using Python as a calculator. Okay, because now if I want to test this, my hypothesis of cutting h by half and the error being cut by the square of that, I can test this over 50 values of h, okay, and look at the error. Okay? All right, so now we saw the true error. We looked at the true error. We can compute the relative error, and that's pretty much kind of it's really straightforward over here. If you want to do the relative error, then we have to, did I ask you for the relative? Yeah, compute the relative error. So essentially take the true error and divide it by the true value and report your results, okay? Does this make sense? Really, the key takeaway here is this definition of the function. Okay, you're not going to lose points for not doing this, okay? But, that's how I would do it, okay? All right. Now, question 2. I don't want to spend too much time here on the programming questions. Okay, the following gas stations were cited for irregular dispensation by the Department of Agriculture with the following data. We have 4 gas stations, A, B, C, and D. And let's say you went and filled up some gas, and you thought that the pump gave you a reading that you filled up 10 gallons, but in fact, the pump dispensed only 9.9 gallons. For the gas station B, you thought you filled up your car with 20 gallons, but in fact, it dispensed 19.9 gallons. Okay? So, just getting ahead, this would be our true value, the actual gasoline dispensed. That's the true value. And the gasoline reading at the pump is the approximate value. Okay? So as we go through the problem. Okay. If you are trying to find out which gas station cheated you the most, which type of error should you look at? Absolute or relative error? Absolute. Why?
You paid for that.
You paid for that. Okay.
Because you can't really contextualize how big the error is without a percentage.
So you're saying we need the relative error?
Yeah.
Yeah. Yes, I agree, the relative error, yeah.
Also, it's likely that they're not like, oh, we're going to take out this many gallons. We're going to, if they're trying to cheat you, they would be trying to go for a rate.
Mm-hmm.
So if you were to put more, it would take out more.
Okay. They're all acceptable. Look, they're all acceptable, but I would use the relative error because look at the gas stations A and B. Both cheated you with 0.1 gallons, right? Both cheated you with 0.1 gallons, but the one that cheated you less is obviously gas station B because you filled out 19.9 gallons, but the other one, you filled out only 9.9, okay? So you did pay for the 0.1 gallon, but relatively you got more gas, right? So we need to do the relative error, okay? Compute the error you chose in the previous question. So again, we can do this with a brute force approach where, I'll show you my solution real quick. But similar to what we did with the derivative problem, we can define an error for gas station A, an error for gas station B, an error for gas station C, and an error for gas station D, and then go through each one of them. And I'll show you kind of my solution over here. True value for gas station A, true value for B, C, D, and then same thing for the observed value. So you can do this, okay? And these are the errors that you will get. Okay, so the one that cheated you the least was gas station D because it had the least relative error. But that's an acceptable solution, but that's not the solution that I would do. The solution that I would do, or the elegant solution, is to actually put all of these stations, all of these numbers in a list, all of these gas stations in a list, okay? So think of it this way. You have a list of true values, the column of the true values, and the column of the approximate values. Imagine we can take those two columns and subtract them from each other and divide by the true value in one variable, okay? And you can do that with Python, with MATLAB, with programming by using arrays, okay? And that's what I want you to start thinking about, rather than doing this kind of tedious process one entry at a time. Now, using lists in Python, so what I claim I want to do is say true values is equal to, what were they? Let's say 9.9. I'm just going to copy them from here. I have them over here. So those are the true values, and the approx values are equal to, okay. Agreed. So I just took these two columns and put them in lists, okay? Now what I want to do to compute an error, I want to take the difference between these two, okay? So let's see what happens if we try to take the difference between these two lists. So let's say true values minus approx values. What happens? You get an error, okay? That's expected, because Python lists do not define the meaning of subtraction. Why? Because Python lists can contain mixed types of variables. They can contain strings, objects, numbers, etc. Okay, so the meaning of minus is undefined, is ambiguous. We need a type of array that only works for numbers so that we can subtract where subtraction is defined. And that type of array is the NumPy array. So I kind of introduced the NumPy array in the EasyPy slides. If you went over those, go over those again. But again, now this is another way to consider NumPy arrays as your standard go-to arrays, because the NumPy array will allow you to do this operation. And it's really easy to introduce a NumPy array. You just simply import NumPy as MP. Okay, that's an alias to NumPy, because I don't want to use numpy.array all the time. And the way you declare an array is simply call numpy.array and put the list inside. Okay, np.array. So now what I claim happens is that we created two types of arrays that could be subtracted from each other. Okay? Yes?
Does it have to be a list inside an array?
It doesn't matter. That's one way to define an array.
Right. Take off the brackets.
No, that will define a multidimensional array. That will define something different. Okay? Just do it this way. Yeah. So now, when I take the difference between these two NumPy arrays, what it does, it takes the difference pointwise. 9.9 minus 10 is minus 0.1. 19.9 minus 20 is minus 0.1. 29.8, and so on. Okay, so we calculated 4 true errors, okay, in one shot. And we can also do now the relative true error, and that's absolute value of true values minus approximate values over true values times 100. And now if you print epsilon t, you get these percentages. Okay? So now remember, the result of an operation between NumPy arrays is a NumPy array. So you do this, the subtraction, it's going to be between two NumPy arrays. It's going to be a NumPy array that contains the difference between NumPy array 1 and NumPy array 2 and element-wise. Okay? Same thing when we divide, and same thing when we multiply. So here we took element-wise, it took the difference and divided by the true value and multiplied by 100. So this value is 1.01%, 0.50%, 0.67%, 0.17%. Okay? That's how you do it in 4 lines of code. Now again, yes.
So do we import the array function from NumPy?
Yeah. And then you can just call it like array, yeah. Yeah, absolutely, whatever you want. All right? Who did this in the homework? Okay, cool. Okay. For those who didn't, it's an opportunity now to start thinking, how can we do it better? How can we do things better? Yeah.
So I was just looking at that, and I got a same results with a slightly different method. But for example, on A, we get an error of 1.01%.
Mhm.
The actual value of the error should be like 1%, right?
The
Based on the numbers we're using.
I don't understand. What?
So if you use the method we have for a approximate true values, you just divide it by the approximate. That would give you 1% error.
Yeah.
So why do we have 1.01011?
Because that's the difference between 9.9 and 10 over 10. It's divided by 9.9, right? That's right. Yeah. So that's the true value. Well, thank you for answering the question. Okay. All right. I'm done with the homework.